Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on tanks, piping, and vessels which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the different types of process piping, list the different types of above-ground storage tanks found in a tank farm, describe the various vessels found in a process plant, describe the effects of corrosion and cathodic protection, explain the factors that influence the selection of materials used to construct a vessel, define the term alloy, describe the various inspection procedures used in a process plant, identify the information found on a vessel sketch, describe a vessel specification sheet. Before starting the course, let us have a look at key terms. Alloy is a material composed of two or more metals or a metal and a non-metal. Blind is a device used in piping to gain complete shutoff. Bonding is described as physically connecting two objects with a copper wire. Bullet is cylindrical-shaped tank with rounded ends that are classified as high pressure. But welded piping is a pipe on which the parts to be joined are the same diameter and are simply welded together. Cone roof tank is an enclosed tank with a conical-shaped roof with vertical walls mounted on a circular concrete pad or directly on the ground. Corrosion is an electrochemical reaction between metal surfaces and fluids that result in the gradual wearing away of the metal. Cryogenic tank has been designed to store liquids below -100 degrees Fahrenheit or -73.33 degrees Celsius. Datum plate is a reference point on the bottom of a tank used to measure liquid level. Dike is a containment wall or ditch that extends around a tank to prevent product loss. Flanges are used to connect piping to equipment or where piping may have to be disconnected, consist of two mating plates fastened with bolts to compress a gasket between them. Flat face flanges are generally used to mate against cast equipment, where bending from tightening bolts might break the flange. Gasket should cover the entire face of the flange. Floating roof tank has an open top and a pan-like structure that floats on top of the liquid and moves up and down inside the tank with each change in liquid level. Gauge hatch is a door in the roof of an atmospheric tank that enables the contents to be measured and that provides some emergency pressure relief. Grounding is described as a procedure designed to connect an object to the earth with a copper wire and a grounding rod. Hemispheroid tank has a rounded or dome-shaped top and vertical walls mounted on the ground or a concrete pad. Jacketed tank, an insulated system designed to hold in heat or cold. Jacketed and gutted piping are two concentric, one inside the other, pipes used when the conveyed fluid must be kept hot. In jacketed piping, the fluid is conveyed through the inner pipe and a heating medium is conveyed through the jacket. Gutted piping is the reverse. Manway is a hatch or port used to provide open access into a tank. Pig is a cylindrical device used to clean out pipes. Most pigs utilize a pig launcher to propel it through the line and into a pig trap. Pipe size is the nominal or named size of a pipe, usually close to the outside and inside diameters of the pipe but identical to neither. The outside diameter of a certain size pipe is constant. The inside diameter will change with the pipe wall thickness or schedule. Pipe thickness is thickness of pipe wall, designated by a schedule number. Schedules 10, thin-walled, 40, 80, and 160, heavy-walled, are common. The schedule indicates a specific wall thickness for one pipe size only. A 3-inch Schedule 40 pipe will have a different thickness than a 4 Schedule 40. The pipe wall thickness increases as the schedule number increases. Radiographic inspection is use of X-rays to locate defects in metals in much the same manner as an X-ray is taken of a broken bone. Raised face flange uses a gasket that fits inside the bolts. Ring joint flange uses only a metal ring for gasketing. Slop tank or off-spec tank is used to store product that does not meet customer expectations. Socket welded piping is a type of piping in which the pipe is inserted into a larger fitting before being welded to another part. Sphere is a circular-shaped tank with legs designed to contain high-pressure liquids or gases. Spheroid is a circular tank with a flat bottom resting on a concrete pad or ground. Stress corrosion cracking is a mechanical chemical type of deterioration associated with steel. Tank farm is a collection of tanks used to store and transport raw materials and products. Traced piping is used when the conveyed fluid must be kept hot, usually has a copper tubing containing steam or hot oil. Vessel design sheets identifies the factors entering into the selection, use, and need for periodic inspection of materials used to make vessels. Tank farm. A tank farm is best described as a collection of tanks designed to safely store and transport raw materials and products. These materials can be brought in from pipelines, barges, ships, or trucks. Above-ground storage tanks, ASTs, come in a variety of designs that can be classified as low, medium, or high pressure. Tank farms can safely store liquids or gases. Manufacturer code stamps on each tank will provide detailed information about the design specifications, pressures, temperatures, etc. that the tank should be operated at. Some tank farms include underground salt domes, caverns, and other below-ground storage systems. Process technicians are required to safely operate and maintain each of the complex storage and transfer systems in a tank farm. This picture shows a typical tank farm. Every tank farm will have a list of the chemicals stored on site and a corresponding material safety data sheet, MSDS. Safely handling and storing chemicals requires structured training and financial resources to maintain the integrity of the tanks, pipes, valves, pumps, and instrumentation. New technicians train from 3 to 6 months before being assigned to operate a complex system. During the training process, the trainee works with a senior technician to learn basic lineups, standard operating procedures, safety rules and regulations, and sampling techniques. Process tanks and storage systems are equipped with the latest in modern process control. Process variables include flow rate, pressure, temperature, composition, and level. Pigging. Technicians use specialized equipment to clean residues out of pipelines. The basic components used in this procedure include a pig launcher, pig, and pig trap. The pig launcher utilizes fluid pressure to launch a projectile called a pig through the pipe. A pig trap, designed to catch the dirty pig, is placed at the end of the pipe. This picture illustrates the different type of pigs utilized in this procedure. Tank designs and categories. Common names for tanks include cone roof, floating roof, internal or external, spheres, spheroid, bullets, hemispheroid, bins, silo, open top, or double wall. Technicians also refer to tanks as the feed tank, vaulted tank, elevated tank, recovery tank, surge tank, blend tank, cryogenic tank, jacketed tank, or blanketed tank. Process technicians use strapping tables to calculate the volume in a tank. A 55-gallon barrel typically holds about 42 gallons. If a tank is rated as a 5,000-barrel tank, it can safely store 210,000 gallons. Tanks of various types are used for the storage of raw materials and finished products. Since these tanks, called tankage, represent a large concentration of value, the protection and safe operation of storage tanks are important. It is necessary that the operators utilizing storage tanks be completely familiar with the tankage and related equipment. Cryogenic tanks are designed to store liquids below -100 degrees Fahrenheit or -73.33 degrees Celsius. Tanks used to store off-specification product are referred to as slop tanks or off-spec tanks. There are various types of tanks, each of which has its own advantages and disadvantages. The type of tank to be used is generally determined by the product to be stored and pressure, measured as pounds per square inch gauge, PSIG. Tanks can be divided into 4 general categories: atmospheric tanks, low-pressure tanks, 0 to 2.5 PSIG, medium-pressure tanks, 2.5 to 15 PSIG, and high-pressure tanks, above 15 PSIG. This picture shows the different types of tanks found in the chemical processing industry. Atmospheric tanks can have a cone roof or a floating roof. Process technicians refer to a tank as being atmospheric when it is properly vented or designed to be run at 14.7 psia, pounds per square inch absolute, or zero gauge pressure, that is, 0 psig. Floating roof tanks. A floating roof tank has an open top and a pan-like structure that floats on top of the liquid and moves up and down inside the tank with each change in liquid level as shown in picture. A close clearance is maintained between the roof and the shell of the tank. The opening is sealed by means of a flexible curtain-like fabric attached to the roof and to steel-bearing surfaces called shoes. The shoes slide on the shell and are kept in contact with the shell by means of a suitable mechanism. There are three basic types of floating roofs: pan type, pontoon type, and double deck. John H. Wiggins invented and built the first practical floating roof in 1921. A pan type, it featured a deck of a single thickness with a vertical cylindrical rim at the periphery or outer edge. The deck is coned slightly toward the center and is provided with radial rafters and trusses to give it stiffness. Today, the pan roof is used only in areas of low rainfall because the roof will tip and sink when loaded unevenly with water or snow. The pontoon type of floating roof has an annular, ring-shaped pontoon around the outer edge and a deck of single thickness at the center. The annular pontoon at the outer edge provides airspace insulation for a large area of the liquid surface, which is helpful in retarding boiling of the product. The pontoon roof is quite stable because rainfall will run to the center and cannot make an uneven load near the edge of the roof. Likewise, a leak in the center section of the roof will not sink the roof or make it unstable. The pontoon is divided into compartments so that a leak in one compartment is confined to a small area and the remaining compartments will be buoyant and support the roof. The area of the pontoon will vary between 25% and 55% of the roof area. The pontoon roof is the most common type of floating roof in use today. The double-deck floating roof has a double deck over the entire liquid surface. The space between the decks is divided into compartments so that a leak will not sink the entire roof. Of course, the double-deck roof is more buoyant than the other types of floating roof, and the airspace between the decks provides an insulation barrier over the whole roof. This type of roof is the most expensive of the three types. Other types of atmospheric tanks. There are other kinds of atmospheric storage tanks, but they are not in common use. The open-top storage tank is used to store water for auxiliary firefighting purposes. The breather roof tank has a flexible steel diaphragm in place of the conventional cone roof. The diaphragm rests on a special set of roof supports so that when it is in the down position it is below the top of the tank. The roof is fastened at the edge, but it is not fastened to the framing, so it can flex up and down for a distance of about 20 inches as the air-vapor mixture in the tank expands and contracts. A roof of this type has very little conservation value and is not recommended for a tank that is filled and emptied many times during the year. It is used primarily for standing storage. The vapor dome roof looks like a cone roof tank with a hemisphere located at the center of the roof. Inside the hemisphere is a membrane of the same shape attached by its outer edge to the equator of the vapor dome. This membrane is free to hang downward in the form of a hemisphere. Hence, the movement of the membrane is equal to twice the volume of the hemisphere. Umbrella roof tanks are very similar to cone roof tanks except that the roof is rounded to a convex shape. Beams may support the roof, although internal supports are also used. Umbrella roof tanks typically have small diameters. Pressure tanks. Pressure storage tanks are used to store volatile liquids, which have a reed vapor pressure greater than 18 pounds per square inch, psi. There are three types of pressure storage vessels: drums, spheres, and spheroids. Drums are cylindrical vessels with ellipsoidal or hemispherical ends built to withstand a given internal pressure. Usually, a drum is supported in the vertical position on a concrete foundation or in the horizontal position on two or more concrete piers. Spheres, as we use the term, are pressure vessels shaped like a sphere and supported above grade on large tubular columns. A sphere 65 feet in diameter will have a volume of 25,000 barrels. A sphere has a more economical shape than a drum for the storage of liquid under relatively high pressure. Spheroid tanks are similar but have a somewhat flattened top and bottom. Cone roof tanks, low to medium pressure. A cone roof tank has a fixed, slightly conical roof, one or more inside support columns, and a flat bottom. Cone roof tanks are used to store low vapor pressure stocks. Cone roof tanks are designed to operate within a range of about 1 inch of water pressure to 1 inch of water vacuum. The welded joint where the roof joins the shell is purposely made weaker than other joints so that it will burst and relieve pressure without spilling the tank contents. This design helps confine the fluid should a fire or explosion occur inside a tank. Hemispheroid or dome tank, low to medium pressure. Hemispheroidal tanks can be classified as medium pressure tanks, 2.5 to 15 psig. This type of tank is typically used for the storage of higher volatility products. For this reason, hemispheroid tanks are a popular choice in the chemical processing industry. This picture is an example of a hemispheroidal tank. A hemispheroidal tank or dome-shaped tank has a rounded or dome-shaped top and vertical walls mounted on the ground or a concrete pad or foundation. Breathing. As a fixed roof tank is filled, the air or vapor in the tank is expelled through a vent. As fluid is withdrawn, air enters the tank through the vent to replace the volume of liquid being withdrawn. To a lesser extent, this breathing action also takes place when the vapor in the tank expands or contracts from heating and cooling. Sunlight and warm days are sufficient to cause some expansion of vapor, and cooling at night or during a rainstorm will cause contraction of the vapors. Flame arresters. In tanks that store flammable materials, the vapor expelled by filling or heating is sometimes mixed with air, oxygen, in the proper proportions to be ignited. The vents are equipped with a flame arrestor to prevent the possibility of fire reaching the contents of the tank. Flame arresters are not designed to prevent flame passage indefinitely, and it is important to extinguish any fire at a flame arrestor immediately. Since the small passages in a flame arrestor element may plug from corrosion or foreign objects, the elements are cleaned on a regular schedule. Manways and manholes. The chemical processing industry uses manways as access hatches or ports into and out of tanks and vessels. These are used for visual inspection and access for cleaning. Manways are typically hinged for easy access. Gaskets are used to provide a positive seal, and a series of bolts and nuts are used to secure the door to the vessel. Opening, blinding and confined space entry permits are required for entry into a vessel. The term manhole is used to describe a circular access port into below-grade systems like sewers or tanks. Manhole covers are typically not hinged. Frequently the terms manway and manhole are interchanged. Conservation vents. Fixed roof tanks that store volatile fluids are often equipped with a conservation vent as shown in picture. A typical conservation vent is equipped with two valves having weighted discs to regulate pressure during operation. The exhaust valve will not open until a slight positive pressure is reached in the tank, and the intake valve will not open until the tank is under a slight vacuum. Controlling the pressure in the tank reduces loss of vapors. Gauge hatches. Gauge hatches as shown in picture are provided in the roofs of atmospheric tanks to enable the contents to be measured. A secondary function of a gauge hatch is to provide some emergency pressure relief. Except when they are in use, gauge hatches should be kept closed to prevent loss of vapors, fire hazards, and entry of rainwater. Hatches should not be weighted or otherwise restricted from opening because restricting their ability to open eliminates their function as a pressure relief device. The datum plate directly below the open hatch is used as a reference point when a technician is measuring liquid level with a gauge line. Water draws. Water draw valves are provided at the lowest point in the tank bottom. They are used to remove water that is settled to the bottom of the tank and may be used to completely drain the tank. Gas blanketed tanks. Depending on the vapor pressure and temperature of the stock in an atmospheric tank, the vapor space may be filled with varying mixtures of vapor and air. The vapor space in tanks storing materials having a low vapor pressure at the storage temperature is usually too lean to explode. The vapor space in tanks storing very volatile materials is usually too rich to explode. In some tanks, however, the vapor space would be nearly always in the explosive range if air were allowed to enter. Gas-blanketed tanks are used to store these hazardous feedstocks. They are also used for other stocks when contact with air or moisture would be harmful to the product. In general, gas-blanketed tanks are similar to other types of fixed-roof tanks except that they are equipped with a supply line for the gas blanket and a regulator to control the pressure. Traditional and modern diking techniques. A dike is best described as a containment wall or ditch that extends around a tank to prevent product loss. A variety of safety designs have been proposed. Examples of these can be found in picture. Dikes are composed of earth, concrete, or metal. Firewalls and trenches are also used in diking designs. Piping. Piping in a chemical plant is used to convey all kinds of fluid materials. It constitutes approximately 30% of the initial investment for a new process plant. The materials used in piping construction are chosen to withstand the temperature, pressure, and other properties of the fluids being conveyed. Some other factors to be considered are codes and specifications, stress factors, layout or routing, and expansion flexibility. Commonly used materials include steel of different alloys, cast iron, aluminum, copper, and plastic compositions. Since metal piping, particularly steel, is the most common, we need to know something about its characteristics. Bonding and grounding tanks, pumps, and piping. A static electric spark can be an ignition source and cause fire or explosion. This takes place when an electric spark discharges across a certain distance between a charged body and an uncharged body. Flammable liquid containers can build up static charges as the material is pumped in. Fluid movement of any type can produce a similar effect. The chemical industry has found two methods to prevent fire hazard from occurring: bonding and grounding. Bonding is achieved by physically connecting two objects together with a copper wire. Grounding is a procedure designed to connect an object to the earth with a copper wire and a grounding rod or grounding device. Underground water pipes can also function as a grounding device. Grounding provides an alternate path for the electricity to flow. When two objects are connected, a spark cannot jump between them. Instead, the electricity flows to the grounding device, that is, the rod or water pipes, and discharges the object to the earth. Corrosion. Corrosion is described as an electrochemical reaction between metal surfaces and fluids that results in the gradual wearing away of the metal. In addition to strength requirements, equipment design also takes into consideration corrosion, that is, metal loss. Knowledge of prior experience under closely related environmental conditions is necessary in order to establish the amount of corrosion that can be expected. Where severe corrosion is not anticipated, 1/8 inch of extra metal is added. In cases where severe corrosion is anticipated, either a greater amount of metal is used, or more corrosion-resistant metal is selected for service. In some process plants, corrosion is constantly in action. It deteriorates equipment, interrupts production, and causes accidents. Corrosion attack manifests itself in many ways, such as general loss of metal, pitting, grooving, cracking, or other kinds of selective attack. Attack may be greatly influenced by minor constituents in the metal or by mechanical, electrical, chemical, or biological factors in the environment. Improper operation also can affect corrosion rates. Typical examples are increasing temperature above design, using an incorrect amount of neutralizers and inhibitors, failing to drain water from equipment during shutdowns, using improper mixing in treating processes, and failing to drain water draws. Cathodic protection. Electrochemical corrosion control in the chemical processing industry is best taken care of using cathodic protection. Electrochemical corrosion causes tanks and pipes to prematurely corrode and fail. Cathodic protection utilizes a direct current device from an external source to counter the discharge of a metal submerged in a conducting medium. Typical conducting mediums include soil and water. The base of any above-ground storage tank is vulnerable to electrochemical attack and corrosion. Cathodic protection utilizes two different methods. Use of sacrificial anodes. Use of impressed current anodes. In both cases, the anodes are placed under or around the tank. Each anode is attached securely to the tank. Sacrificial anodes corrode in the place of the tank and will eventually need to be replaced, while the impressed current anodes do not corrode. When current flow is open, the system can protect the tank indefinitely. Steel and other types of pipes. Most piping used in process units is carbon steel, primarily because it is fairly economical and has a wide temperature range. Carbon steel is used from -20 degrees Fahrenheit or -28.88 degrees Celsius to around 800 degrees Fahrenheit or 426.66 degrees Celsius. Specially heat-treated carbon steel is used in a temperature range of -21 degrees Fahrenheit or -29.44 degrees Celsius to -50 degrees Fahrenheit or -45.55 degrees Celsius. Farther down the temperature range, Type 304 stainless steel or 3-inch nickel is normally used. The temperature range of 3-inch nickel is -51 degrees Fahrenheit or -46.11 degrees Celsius to -150 degrees Fahrenheit to -101.11 degrees Celsius. Type 304 stainless steel is used in services from -151 degrees Fahrenheit or -101.66 degrees Celsius to -320 degrees Fahrenheit or -195.55 degrees Celsius. The stainless steels at very low temperatures do not become brittle as regular carbon steel does. Stainless steel is also used in some high-temperature applications such as tube supports in furnaces. Stainless steel when coupled to carbon steel can cause problems because of its expansion rate, which is approximately 150% that of carbon steel. Some low alloys like carbon, moly, and chrome are used in high-temperature service such as furnace tubes. These alloys are made for operations over 800 degrees Fahrenheit to 426.66 degrees Celsius. An alloy is a material consisting of two or more metals or a metal and a non-metal. A low alloy is one that has a relatively small amount of the secondary material. Steel pipe is manufactured in various diameters and wall thicknesses. Pipe sizes are identified by the pipe's nominal size. Nominal means in name only, which is usually different from their actual inside and outside diameters as shown in picture. For example, a 3.5-inch pipe has an outside diameter of 4 inch and an inside diameter somewhere between 3 and 4. Most pipe used in plants is 1/2 inch, 3/4 inch, 1 inch, 11/2 inch, 2 inch, 3 inch, 4 inch, 6 inch, 8 inch, 10 inch, 12 inch, and 14 inch and higher. When a pipe has an outer diameter of 14 inch or over, the outer diameter is the same as the nominal pipe size. Sizes of 1/5 inch, 11/4 inch, 21/2 inch, 31/2 inch, and 5 inch are not usually used. The pipe thickness of the pipe wall is designated by a schedule number. Schedules 10, thin-walled, 40, 80, and 160, heavy-walled, are common. The schedule indicates a specific wall thickness for one pipe size only. A 3-inch Schedule 40 pipe will have a different thickness than a 4 Schedule 40. The pipe wall thickness increases as the schedule number increases. Cast iron piping. Cast iron pipe and fittings are used to convey non-flammable fluids in some areas. The sizes and thicknesses of cast iron pipe are similar to those of steel pipe. Because iron becomes brittle when it is exposed to fire and then sprayed with water, there is a good possibility that the cast iron would break under those conditions. For this reason, cast iron piping is not used in hazardous areas, nor is it used to handle flammable materials in any area. Joining pipes. Almost all piping in critical services is joined together by welded joints, which provide much more strength and less chance for leaks than do threaded joints. For piping that is not critical, as far as pressure or contents is concerned, piping with threaded joints is generally much cheaper and easier to install than is piping with welded joints. Screwed piping. Small pipes are commonly joined by the use of tapered pipe threads. The threads are cut into both male and female parts of the joint and are tapered to provide a tight fit. Usually a thread compound, or Teflon tape, is applied to the threads to aid in sealing the joint and for lubrication in connecting the joint. Since metal is removed in cutting threads, the weakest part of screwed piping is usually the joints. Screwed piping as shown in picture is used in sizes up to 2 inch for handling non-hazardous materials. Welded piping. 2 types of welding may join piping as shown in picture. In butt welded piping, the parts to be joined are the same diameter and are simply welded together. In socket welded piping, the pipe is inserted into a larger fitting before being welded. Socket welded fittings are usually used in 2-inch size and smaller because there is less possibility that stray weld metal will obstruct the flow area. Butt welding is used in all sizes, but particularly in 2-inch size and larger. Flanges. Flanges are used to connect piping to equipment or where the piping may have to be disconnected. They consist of 2 mating plates fastened with bolts to compress a gasket between them. The 3 common types are shown in picture. Flat face flanges are generally used to mate against cast equipment, where bending from tightening bolts might break the flange. A gasket should cover the entire face of the flange. Raised face flanges use a gasket that fits inside the bolts, and ring joint flanges use only a metal ring for gasketing. Flanges are made in various thicknesses and for various bolt sizes according to the pressure and temperature of the service. Ratings of 150 pounds, 300 pounds, and 600 pounds are common in chemical plants. Fittings. Elbows, T's, flanges, valves, and other piping components are made to mate with screwed, flanged, and welded piping discussed in the previous sections. These items are also made in various weights and are constructed for certain pressure and temperature ratings. Jacketed, gutted, and traced piping. A special type of piping used where it is necessary to keep the conveyed fluid hot is jacketed, gutted, or traced piping. Both jacketed and gutted piping have 2 concentric, one inside the other, pipes. In jacketed piping, the fluid is conveyed through the inner pipe and a heating medium is conveyed through the jacket, the outer pipe. Gutted piping is the reverse, the fluid is conveyed through the outer pipe and the heating medium is conveyed through the inner pipe. The general practice involved with steam tracing includes wrapping copper tubing around the process pipe and covering it with heat transfer cement or insulation. Hot oil tracing systems are used when the process fluid is hotter than the plant's steam system. Low-pressure steam or hot oil is passed through the copper tubing during operation. This procedure is often used to winterize a unit when temperatures are expected to drop below freezing. A negative aspect of steam tracing occurs when the copper tubing sweats under the insulation and, as a result, traps moisture next to the piping. Paddle and figure-8 blinds. Blinds are one of the main means used to gain a complete shutoff in piping. 2 types of blinds are generally used in plants. The first, called a paddle blind, is nothing more than a piece of metal thick enough to be subjected to and withstand a specific pressure. The paddle blind is inserted between 2 flanges, with a gasket on each side, and tightened. The second type of blind, the figure-8 blind, is designed to be installed inside the piping. On one end of the blind is an opening to be used as a spacer between 2 flanges when the blind portion is not in use. The figure-8 blind has an advantage in that it is always at the location of use, whereas the paddle blind, when not in use, can be misplaced. Double block and bleed. A double block and bleed system is frequently used to stop flow. This is not considered a complete shutoff, however. The double block and bleed consists of two valves in line with a smaller valve opening to the atmosphere between the two line valves. Vessels. It is important for operating people to understand the limitations of equipment in order to ensure uninterrupted operations. This section outlines some of the factors entering into the selection, use, and need for periodic inspection of materials used to make vessels and other plant equipment. Vessel documentation and design. Each vessel will include a code stamp that will indicate high pressure and high temperature ratings, manufacturer, date, type of metal, storage capacity, and special precautions. Most vessel documentation includes strapping tables that will allow a technician access to data that can be used to identify capacity. For above-ground storage, the ASME, American Society for Mechanical Engineers, Code, Section 8 governs vessels that have pressures greater than 15 psig. Common storage designs include spheres, spheroids, horizontal cylindrical tanks, drums, bins, and tanks with fixed and floating roofs. Tanks, drums, and vessels are typically classified as low pressure, high pressure, liquid service, gas service, insulated, steam traced, or water cooled. Wall thickness and shape often determine the service a vessel can be used in. Some tanks are designed with internal or external floating roofs, double walls, dome or cone roofs, or open top. Earthen or concrete dikes often surround a tank and are designed for containment in the event of a spill. Spherical and spheroidal storage tanks are designed to store gases or pressures above 5 psig. Spheroidal tanks are flatter than spherical tanks. Horizontal cylindrical tanks or drums can be used for pressures between 15 and 1000 psig. Floating roof storage tanks are used for materials near atmospheric pressure. In the basic design, a void form between the floating roof and the product, forming a constant seal. The primary purposes of a floating roof are to reduce vapor losses and to contain stored fluids. In areas of heavy snowfall, an internal floating roof is used with an external roof because the weight of the snow would affect the seal. Vessel thickness. If the original design thickness of all pressure retaining parts in a plant could be maintained and the process conditions held constant, the unit would not require periodic inspection and operation could be continuous. Since this is rarely possible, it is important to know what factors affect the initial required thickness of operating equipment and one factor, corrosion, that can reduce the thickness of equipment. Essentially, the thickness of pressure-retaining equipment depends on the diameter of the pipe, vessel, exchanger, or other equipment, pressure, temperature, strength of material used, and anticipated corrosion rates. A 1/8-inch corrosion allowance is normally provided. Of these, the operator has control of pressure, temperature, and process changes that might affect the amount of corrosion. Pressure. The equipment is designed for normal operating pressures plus an incremental increase in pressure to allow for operating upsets. The relief valve on the equipment or in the system is set to relieve when the design pressure is exceeded and is provided for equipment protection and safety of personnel. Blocking an equipment unprotected by relief valves, unofficially increasing the relief valve set pressure, and blocking in cooling water in exchangers while in service are only several possibilities of creating hazardous conditions in the unit. The operator should be aware that such unsafe practices can exceed design conditions and may cause failure. Temperature. In general, the strength of metals decreases as temperature increases. Reduction in strength usually starts at 650 degrees Fahrenheit or 343.33 degrees Celsius and becomes critical in the range of 950 degrees Fahrenheit or 510 degrees Celsius to 1000 degrees Fahrenheit or 537.55 degrees Celsius in the case of carbon steel. For example, the strength of low-carbon steel is reduced 22% when temperature is raised from 950 degrees Fahrenheit to 975 degrees Fahrenheit or 510 degrees Celsius to 523.88 degrees Celsius. Similarly, because of this decrease in strength as temperatures increase, it is important that pressure in equipment be reduced and exposed metal surfaces cooled with water during fire conditions. Besides affecting strength, temperature also has a profound effect on corrosion rates. For example, in streams containing sulfuric acid, a 20 degrees Fahrenheit or 6.66 degrees Celsius increase in temperature can double corrosion rates. Materials: carbon steel, alloys, and non-ferrous alloys. The metals described in this section are those most commonly used in chemical plants. There are, of course, a great many other metals that are used, but they are not covered owing to space limitations. Low-carbon steel. Fortunately, low-carbon steel, which is familiar to everyone, is a very satisfactory material for most plant applications. It is relatively inexpensive yet provides the strength, workability, and welding properties required. Most of the equipment used in a plant is made of this versatile material. The steel used for equipment is low in carbon, 0.3% or less, sulfur, and phosphorus, and contains sufficient manganese to offset the effect of sulfur. It may also contain small quantities of silicon or aluminum. The low carbon content promotes ductility and weldability. Although low-carbon steel is suitable for the majority of services, a number of other materials have been developed to cope with the severe conditions encountered as new processes were developed. However, none of these materials are suitable for all services. Low-alloy steels. As the operating temperature of equipment increases above 650 degrees Fahrenheit or 343.33 degrees Celsius, the strength of low-carbon steels decreases. This decrease in strength becomes very pronounced between 950 degrees Fahrenheit and 1000 degrees Fahrenheit or 510 degrees Celsius and 537.77 degrees Celsius. For example, at 950 degrees Fahrenheit and 1000 degrees Fahrenheit or 510 degrees Celsius and 537.77 degrees Celsius, the strength of low-carbon steel is about 1/3 and 1/6, respectively, of its room temperature strength. As a result, the strength of this type of steel becomes so low that it is not a satisfactory material. The strength and resistance to oxidation, rushing, required for these conditions are secured by adding small amounts of alloying elements. Molybdenum in quantities as small as 0.5% greatly increases the strength above 900 degrees Fahrenheit or 482.22 degrees Celsius. Chromium is added in amounts up to 9% to combat the tendency to oxidize at high temperatures and to resist corrosion from materials that contain sulfur. These steels still retain much of the ductility, toughness, and weldability of low-carbon steel but require more extensive and careful heat treatment when welded. The chrome alloys are used in pressure vessels, piping, furnace tubes, and exchangers operating at high temperatures and pressures. Some of the processes used in refining and chemical plants employ hydrogen at high temperature or high pressure or both. Low-carbon steel normally becomes brittle in this service above 500 degrees Fahrenheit or 260 degrees Celsius. Embrittlement is prevented by using steels that contain small amounts of chromium or molybdenum or both. When it is necessary to operate equipment at very low temperatures, low-carbon steel becomes an unsatisfactory material. Operating above -20 degrees Fahrenheit or -28.88 degrees Celsius, it is a tough and ductile material. Below it, the steel begins to lose its ability to resist sudden shock. Most of the plain carbon steels are ductile to -20 degrees Fahrenheit or -28.88 degrees Celsius, and suitable heat treatment could be used to -50 degrees Fahrenheit or -45.55 degrees Celsius. Adding small amounts of alloying elements lowers the temperature at which steel becomes brittle. Nickel is the most common metal added to steel for this purpose. The addition of 3% to 5% nickel will produce steels that remain tough to -150 degrees Fahrenheit or -101.11 degrees Celsius. High alloy steels. The properties of steel can be varied widely by small additions of other elements to produce steels that are satisfactory for most services. In some cases, however, it is not possible to produce steel that is satisfactory for a particular service by adding small amounts of other elements, and larger quantities of alloying elements are necessary to produce the desired characteristics. Steels that contain 10% or more of alloying metals are generally called high-alloy steels. The members of this group most often used in plants are chromium steel and austenitic steel, that is, stainless. Chromium steels. Chemical components containing appreciable amounts of sulfur compounds become quite corrosive to steel at temperatures ranging from about 550 degrees Fahrenheit to 850 degrees Fahrenheit or 287.77 degrees Celsius to 454.44 degrees Celsius. Chromium steels withstand this type of attack very well, but in some cases the low chromium alloys previously described are not resistant enough to be economically attractive. In these cases, alloys containing from 12% to 17% chromium are used. The 17% chrome steels were used rather extensively initially for severe sulfur corrosion, but they had a tendency to become brittle after extended heating cycles in the 700 degrees Fahrenheit to 1000 degrees Fahrenheit or 371.11 degrees Celsius to 537.77 degrees Celsius range. Their primary use is now largely confined to pump and compressor parts. The 12% chromium materials are widely used as protective linings in steel equipment, thermowells, and valve trims subject to this type of sulfur corrosion. Austenitic or stainless steels. When both nickel and chromium are added to steel in amounts totaling somewhat over 20%, the microscopic structure undergoes a pronounced change. The small grains of which steel is composed solidify in a form known as austenite, which behaves in many respects quite differently from the steels previously described. The most common composition of stainless steel is commonly referred to as 18-8. This name comes from the fact that this stainless steel contains about 18% chromium and 8% nickel. Other members of the family contain higher amounts of either or both of these elements, and some contain small amounts of other elements. Molybdenum is an additional element commonly used. An outstanding characteristic of this group of steels is resistance to rusting when exposed to the atmosphere, as well as resistance to corrosion by a wide variety of chemicals. They also retain much of their strength and have excellent resistance to oxidation at extremely high temperatures. In process units, they are widely used for brick hangers and tube supports in furnaces. Here, the materials flowing through them cool the tubes, but their supports are not and must maintain adequate strength and oxidation resistance at firebox temperatures. In other applications, these steels are used when it is necessary to process materials at very low temperatures. They remain tough and ductile at temperatures far below those at which low-carbon steel becomes brittle. Although the stainless steels are extremely useful in plants for many severely corrosive and high-temperature services, they have some limitations that make them impractical for certain applications. Two conditions that cause these steels to deteriorate are stress corrosion cracking and a high coefficient of expansion. Stress corrosion cracking is a mechanical chemical type of deterioration. Many materials, even low-carbon steel, are subject to it in particular critical environments. In plants, the most familiar occurrence is the cracking of stainless steels in chloride environments. The cracking is usually across the metal grains, and there is little metal loss from corrosion. The other undesirable characteristic of stainless steel is its high coefficient of expansion. When stainless steel is heated, it expands at a rate approximately 150% of that of steel. This expansion becomes a problem whenever stainless steel is used in close contact with other metals. At high temperatures, great internal strains can be produced because the two materials expand at different rates. Non-ferrous alloys. A metal or alloy that contains little or no iron is called a non-ferrous material. There are a great many elements other than iron that are metals in their pure form, and the combinations of these as alloys are almost limitless. Some of these alloys are rather widely used. Nickel alloys. In a few locations around a chemical plant where extreme resistance to chemicals is required and the stainless steels are unsatisfactory, a group of alloys containing large amounts of nickel are used. These alloys usually contain additions of iron, copper, aluminum, chromium, cobalt, and molybdenum. Some typical examples of these alloys are Monel, Hastelloy, and Inconel. These alloys are used in a variety of services that involve acids and caustics. For example, Monel is used in hot sodium hydroxide or hydrochloric acid service. Copper alloys. Brass is the term used to describe a family of alloys of copper and zinc. The copper content ranges from 90% to about 60%, with the balance being zinc. Some brasses have small amounts of other elements such as lead, tin, antimony, arsenic, and phosphorus. Brasses are widely used because of their resistance to corrosion from water containing various impurities that are corrosive to steel. They are weaker than steel and lose much of their strength when heated. They are not normally used at temperatures above 450 degrees Fahrenheit or 232.22 degrees Celsius. Brass is most commonly used in condenser or cooler tubing when water is the cooling medium. Some brasses, notably those containing lead and antimony, have good anti-friction properties and are widely used as bearing materials in pumps and compressors. The bronzes are a second family of copper alloys. These alloys contain 90% or more copper. Aluminum, tin, or silicon makes up the balance. Aluminum and silicon bronzes are more resistant to salt water than brass and are widely used as condenser tubing when salt water is the cooling medium. There are a number of copper-nickel alloys. One of these, called cupronickel, contains 70% copper and 30% nickel. Cupronickel is used in condenser tubing when the cooling water has extreme concentrations of salt. Aluminum alloys. The outstanding characteristics of aluminum are its good resistance to corrosion from sulfur compounds and its resistance to continuous oxidation when exposed to the atmosphere. Because of its resistance to corrosion by sulfur, aluminum is used for internal parts of equipment processing high-sulfur stocks. It is often used in sheet form to protect and weatherproof insulation on pipe and towers because of its resistance to atmospheric corrosion. There are many alloys of aluminum, which contain small amounts of other metals that greatly increase its room temperature strength. This strength in most aluminum alloys decreases rapidly with increasing temperature. Aluminum coatings over iron-based alloys have been used rather extensively in recent years to protect equipment from high-temperature sulfur and hydrogen sulfide corrosion as well as high-temperature oxidation. Lead alloys. Lead is a heavy, extremely ductile, relatively weak material that melts at a rather low temperature. It is used as a lining material in sulfuric acid treating equipment. Inspection. Prolonged and safe operation depends upon good inspection practices for assurance that equipment is being maintained in a safe condition and that off-stream time is reduced to a minimum by anticipation of necessary repairs. In general, the scope of work includes all pressure vessels, heat exchangers, storage tanks, process piping, pumps, relief valves, furnace tubes, fittings, breechings, stacks, and tube supports. Any equipment subjected to pressure or temperature extremes must be inspected periodically. Power boilers and auxiliaries are subject to state regulations and inspection. Representatives of an insurance company may also inspect the boilers. Plant inspectors make joint inspections with state and insurance company inspectors and keep records for reference. Inspecting pumps and compressors is an important function of operators as well as maintenance and engineering personnel. The inspector studies the condition peculiar to each piece of equipment. The nature of the material contained, the pressure, temperature, flow conditions, and other factors may cause or contribute to deterioration of equipment. Familiarity with operating conditions and knowledge of the materials of construction are essential. A study of conditions and materials leads to planning and actual performance of inspection, at which time the true condition of the equipment is determined. The scope of inspection work also includes keeping records, reporting results, recommending repairs and methods of repair, assisting in planning turnarounds, and determining safe working limits for equipment. When inspection reveals the need for replacement parts, it is important that the new parts be designed in accordance with recognized codes and specifications. Inspection frequency and extent. The frequency and extent of inspection depend on factors such as pressure, temperature, corrosive action of the materials handled, and materials of construction, corrosive allowance, and past experience with the equipment involved. Equipment in high-pressure, high-temperature service subject to corrosion is, of course, inspected frequently. On the other hand, some equipment may require complete inspection only once in 5 years. The frequency and extent of inspection are established independently for each item and are subject to change with changes in operating conditions. In practically all cases, only part of the lines and equipment constituting a unit are inspected. Inspections are scheduled so that complete inspection of the unit will extend over several inspections. Inspection methods and equipment. Visual inspection is the method most generally used and requires no explanation. Experienced inspectors use hammer testing to estimate the metal thickness. The equipment or line is tapped with a hammer and the feel and the sound are noted. The hammering sets up a vibration, and the sound depends on the thickness of the point struck. The feel of the hammer and the extent of denting also give an indication of thickness. Hammering can be used to determine doubtful areas. Other types of inspection, such as drilling or calipering, can be used to obtain an accurate reading in the thin area found by hammering. Transfer or direct reading calipers are used for measuring thickness when the areas being inspected are accessible. A variety of remote reading instruments are available for measuring internal diameters of furnace and exchanger tubes. Measuring through drilled holes, called trepanning, is the most accurate method of determining wall thickness when transfer calipers cannot be used. The thin area is first determined by visual inspection or a hammer test, and a hole is drilled completely through the wall. The thickness is measured through the hole. Holes are closed by threading the opening with a tapered thread and screwing in a tapered plug. Welding may also close holes. Trepanning is used to inspect the welding on new storage tanks or similar equipment. It is also used at times to investigate the nature and extent of defects in plates or welds discovered by previous visual inspection. This method of inspection is no longer used extensively because it has quite generally been replaced by non-destructive radiographic X-ray techniques similar to those used to identify broken bones. Radiography is also used to determine pipe and tube wall thickness. Weld probing is done by a special machine that removes boat-shaped samples from plates. These samples are generally taken to check welding, or the condition of the material sampled. Several electronic sonic devices are available for measuring metal thickness. They are used mainly for determining the shell thickness of pressure vessels, storage tanks, piping, and thick-walled equipment. They have the ability to measure only the thickness of the material contacting the crystal probe or coupled in some manner to the probe. Multiple layers of metal, coke, or other deposits on the opposite side from the probe are excluded from the thickness readings obtained. These instruments are quite reliable if the opposite surface is not too severely pitted or if the material is not less than 1/8 inch thick. An electronic radium source device is also used for measuring metal thickness. This type of instrument gives a rapid examination because no surface preparation is required, as in the case of most electronic sonic devices, and readings are obtained directly in about 30 seconds. Metal temperatures up to 1000 degrees Fahrenheit or 537.77 degrees Celsius will not damage the instrument or seriously affect the accuracy of the measurements. The range is from a maximum of 3/4 inch to 0, with its accuracy increasing near the zero end of the range. This characteristic makes it ideal for examining piping. However, it has its limitations, as it will include in the measurement any coke, liquid, extra layers of metal, or foreign deposits in the pipe or vessel. Also, in severely pitted areas, an average thickness reading will be obtained. Crack or imperfection detectors use a dye penetrant to locate surface cracks in the metals. The technique consists of applying a dye penetrant to the suspected area, washing the surface, and then applying a developer solution. If a crack is present, a bright red line will appear in the white developing coating, locating its position. Magnetic particle inspection is used to detect surface or near-surface flaws in equipment that can be magnetized. A magnetic field is induced, and an iron powder is dusted on the piece to be inspected. The iron powder adheres to the piece at any discontinuity in the magnetic field, thus outlining such defects as cracks, porosity, and inclusions embedded foreign material. Hardness testers of various types are used in the shops and field to determine the hardness of metals. These hardness readings indicate the approximate strength and ductility of material. Vessel design sheets. Vessel design sheets are sketches that include information necessary for the selection, use, and need for periodic inspection of materials used to make vessels. These pictures illustrate vessel design sheets of typical vessels found in process units. Common names for tanks include cone roof, floating roof, internal or external, spheres, spheroid, bullets, hemispheroid, bins, silo, open top, or double wall. Technicians also refer to tanks as the feed tank, vaulted tank, elevated tank, recovery tank, surge tank, blend tank, cryogenic tank, jacketed tank, or blanketed tank. Tanks can be divided into 4 general categories: atmospheric tanks, low-pressure tanks, 0 to 2.5 psig, medium-pressure tanks, 2.5 to 15 psig, and high-pressure tanks, above 15 psig. Depending on the vapor pressure and temperature of the stock in an atmospheric tank, the vapor space may be filled with varying mixtures of vapor and air. The vapor space in tanks storing materials having a low vapor pressure at the storage temperature is usually too lean to explode. The vapor space in tanks storing very volatile materials is usually too rich to explode. In some tanks, however, the vapor space would be nearly always in the explosive range if air were allowed to enter. Gas-blanketed tanks are used to store these hazardous feedstocks. They are also used for other stocks when contact with air or moisture would be harmful to the product. In general, gas-blanketed tanks are similar to other types of fixed-roof tanks except that they are equipped with a supply line for the gas blanket and a regulator to control the pressure. Piping in a chemical plant is used to convey all kinds of fluids, and vessels such as tanks, bins, and drums store the fluids. The materials used in piping and vessel construction are chosen to withstand the temperature, pressure, and other properties of the fluids being conveyed or stored. Pipe data tables can be used to determine the actual inside and outside diameters of pipe of a given nominal size. Vessel design sheets outline some of the factors entering into the selection, use, and need for periodic inspection of materials used to make vessels and other plant equipment. Changes in the thickness of pressure-retaining equipment necessitate periodic inspection. Essentially, the thickness of pressure-retaining equipment depends on the diameter of the pipe, vessel, or exchanger, pressure, temperature, strength of material used, and anticipated corrosion rates. A 1/8-inch corrosion allowance is normally provided. The process technician has control of pressure, temperature, and process changes that might affect the amount of corrosion. The frequency and extent of inspection depend on factors such as pressure, temperature, the corrosive action of the materials handled, the materials of construction and their corrosion resistance, and past experience with the equipment involved. Equipment in high pressure, high temperature service subject to corrosion is inspected frequently. Some equipment may require complete inspection only once in 5 years. Visual inspection is the method most generally used. Experienced inspectors use hammer testing to estimate the metal thickness. Transfer or direct reading calipers are used for measuring thickness when areas being inspected are accessible. A variety of remote reading instruments are available for measuring internal diameters of furnace and exchange tubes. Measuring through drilled holes, trepanning, is the most accurate method of determining wall thickness when transfer calipers cannot be used. Weld probing is done by a special machine that removes boat-shaped samples from plates. Several electronic sonic devices are available for measuring metal thickness. They are used mainly for determining the shell thickness of pressure vessels, storage tanks, piping, and thick-walled equipment. An electronic radium source device is also used for measuring metal thickness. Crack or imperfection detectors use a dye penetrant to locate surface cracks in metals. Magnetic particle inspection is used to detect surface or near-surface flaws in equipment that can be magnetized. Inducing a magnetic field and dusting an iron powder on the piece to be inspected causes the iron powder to adhere to the piece at any discontinuity in the magnetic field. Radiographic inspection is used to locate defects in metals and pipe and tube wall thickness in much the same manner as an X-ray is taken of a broken bone. Hardness testers are used to determine the hardness of metals. These hardness readings indicate the approximate strength and ductility of material. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.